This section is about something called calorimetry. Calorimetry is a way of determining heat flow experimentally. Well, our lab in this unit is actually going to be a calorimetry lab, and so is the virtual lab. The requirement for calorimetry is to isolate the reaction as much as possible from the surroundings. We'll use basically a styrofoam coffee cup to do that. The virtual lab is going to do something much more advanced, which is called a bomb calorimeter. Very, very similar though. Let's talk about how to do calorimetry. The basic equation for calorimetry is Q equals MC delta T. Your book actually says SM delta T, but it's the same thing. Where M is the mass of whatever it is that's reacting. Delta T is the change in temperature. Change in temperature. Okay. This can be either in kelvins or in Celsius. It doesn't matter because, again, that delta, that change in, the size of the degree in Celsius and Kelvin is the same. So when you subtract, it doesn't matter whether you're in kelvins or Celsius. This lowercase c here, which is the thing your book calls S, is something called the heat capacity, or the specific heat. The specific heat is the heat capacity of 1 gram. That's what your book is calling S. Heat capacity basically is the ability of a material to conduct heat. So as you can imagine, different materials have different heat capacities. That's a constant for a particular substance. You can look it up or you can actually calculate it. And the heat capacity has units of joules, capital J, joules. I know you've run into that one before. Grams, Kelvin, or as I say, grams, degrees Celsius. It doesn't really matter. And obviously mass is in grams. The C for water, the heat capacity for water, is one that you use all the time, and it's 4.18. That's the heat capacity for water, joules per gram degrees Celsius, or gram Kelvin. These are really just plug and chug problems. They say to you, you have 5 grams of aluminum. You have 5 grams of aluminum, and you look up the specific heat capacity of aluminum being 0.90 joules per gram degrees Celsius, and you say that the temperature of that piece of aluminum rises from, say, 50 degrees Celsius, or from 25 degrees Celsius to 50 degrees Celsius. Temperature's rising. What is the heat what is the amount of heat that has been gained by the aluminum? This is merely a multiplication. 5 times 0.9 times 25 gives me 112 joules. And of course, there's all kinds of places you could put the unknown and solve for whatever it is they don't tell you. And that's really all that is. Bomb calorimetry, just so you'll know for the lab, has a slightly different equation. It's Q of the reaction is negative C of the calorimeter times delta T. This is a different C. This is basically a constant for the calorimeter. Note the negative sign here because we're talking about the Q for the reaction, which is the opposite in sign for whatever's happening inside the bomb calorimeter. Essentially what you're going to do is you're going to do a reaction where you know the Q, you measure the delta T, and then you solve for that guy for that particular calorimeter you are using. Then once you've done that, that C is a constant for that particular calorimeter, and then you put in an unknown, you measure the delta T, and you can figure out the Q for your unknown. I remember doing that when I was in college. We were allowed to bring in food from the cafeteria to test, because really that's what this is. Another energy unit besides joules is calorie. as in the calories in your food. That's what calories in food are. It's the amount of energy that the body gets from processing that food. Now, let's talk about enthalpy. Enthalpy is delta H. Well, enthalpy is H. Delta H is the change in enthalpy. We can't really measure H. We can measure delta H, the change in H. You'll recall I said in the last video, delta H was a state function. We're going to actually use that to help. Let's say, for example, we have a reaction. Let's go with methane burning in oxygen to give me carbon dioxide and liquid water. You'll notice I'm being very careful to put the states of matter here. It's going to change. Enthalpy will change if these states would be different. Okay, if I put gaseous water there, that would be different. Now, I can look up that the delta H for this reaction, the enthalpy of this reaction, is negative 890 kilojoules. Negative means, remember, that this is exothermic. Heat is being given off by the reaction. Now, enthalpy is what they call an extensive property. That is, it depends on amount. So, it's negative 890 kilojoules for a mole of methane. If I had, say, 2 grams of methane and I wanted to know what the energy of it was, the enthalpy, rather, I can actually do stoic. I could say 2 grams of methane, turn grams into moles, methane 16 grams in 1 mole, and I know that for every 1 mole of methane, it's negative 890 kilojoules of energy that's being given off, of heat that's being given off, and I could do the math and figure out what that was. So this kind of lovely stoic is something that's very, very useful in these kinds of problems. Now you may wonder why the symbol for enthalpy is H, and H stands for heat. So this reaction, for example, is a combustion reaction. So the H, the enthalpy of this reaction, is called the heat of combustion. You'll see that a lot, the heat of combustion, the heat of vaporization, the heat of this, the heat of that. They're all the same, and all the same rules apply. They're just naming the particular kind of reaction that's going on. Now, if I were to be talking about the reverse reaction, water plus carbon dioxide making somehow methane and oxygen, the delta H for that would be identical, but it would be opposite in sign. Energy, because again, that goes back to the first law of thermodynamics, energy is conserved. The heat that's being given off in one direction is absorbed in the other direction, which